Okay, I think we better get started. We've only got a humble number of 8 people with us today, although 25 or so has signed up. They seem to have found other things to do, at least for the time being. So I think we'll get started. Otherwise, we'll get squeezed the other end of it, and people can now keep an eye out and let people join us as they come along. Anyway, good afternoon, everyone. My name is Dr. Ian Todd. I'm the chair of the Irrigation Water Forum and chair of today's event. It's my great pleasure to welcome you to the IWF's second Tea Time talk on the topic of canal lining. Before we start, well, there's a couple of housekeeping notices that I need to highlight. Firstly, you'll be muted for the duration of the presentation, but you'll be able to engage with our speakers through the chat box. After the presentation and during the question and answers, please use the hand icon if you want to ask a question directly to the speakers. I encourage you to submit questions through the chat during the presentation. Please state your organization when you ask a question. That's helpful too. I'd like to inform you that this event is being recorded and will be available on the IWF website within a few days, hopefully. So let's move on to today's tea time talk. As we know, the purpose of a canal is to convey water, but seepage reduces the amount of water arriving at a canal's endpoint. A major challenge for designers and operators or managers of canals is to minimize seepage losses, to minimize seepage. Canal lining is a process to reduce seepage losses from a canal by adding an impermeable layer to the canal's wetted perimeter. In irrigation canals, seepage can be as high as 30 to 50% of the flow. So adding lining to reduce seepage allows irrigation canals to deliver more water. Canal linings are also used to prevent weed growth and reduce sediment deposition, both of which reduce water flow. Lining can also be used to prevent water logging around low-lying areas alongside canals. The topic of today's talk is concrete canvas and GCCM, which stands for Geosynthetic Cementitious Composite Mats, a new lining technology for reducing water seepage from canal infrastructure around the world. The presenters are William Crawford and Simon Lester from Concrete Canvas Limited. Will is a director and co-founder of Concrete Canvas Limited, set up in 2005 to develop and commercialize concrete canvas technology. Will has a master's in mechanical engineering from Bristol and a joint master's from Imperial College, where he co-invented concrete canvas, as well as several other award-winning designs, including an innovative low-tech fridge for developing countries. Will has recently awarded a silver medal by the Royal Academy of Engineering, awarded to individuals in recognition of their outstanding contributions to British engineering. Simon is the new product introduction manager at Concrete Canvas Limited, where he's worked since 2016. This follows an extensive career in civil engineering, contracting, design, consulting, and project management since graduating from the University of KwaZulu-Natal in 2005 with a Bachelor of Science Civil Engineering degree. Simon is a professionally registered civil engineer and also holds a Bachelor of Science degree in Geography and Psychology. So over to Will to start the presentation.
Brilliant, thank you very much, Ian. I think you'll need to enable me to share my screen.
There you go.
While you do that, I'd like to thank you, Ian, and thank you, Peter, and thank the IWF for the opportunity of presenting today. And thank you to all the attendees as well. Hopefully we might pick up a few more before the end of the hour. The presentation is about 45 minutes, so there should be 10 or 15 minutes at the end, and we'd welcome your questions. So I should now be able to share my screen. Okay, hopefully everyone can see that. Fantastic. So, as Ian said, the title of the presentation today is An Introduction to Concrete Canvas, a New Canal Lining Technology. And Ian has already given a very generous introduction to both myself and Simon, who will both be presenting. In terms of the agenda, I'm going to start off just introducing a bit of background to the company and the material, how we came up with the invention. I'll then go on to talk about some of the properties of GCCMs, which I appreciate is quite an acronym. It stands for Geosynthetic Cementitious Composite Mats. And this is the new material class that concrete canvas falls into. And then I'll hand over to Simon, who's going to introduce a new material that we've developed specifically for lining irrigation canals. And we would very much appreciate your feedback at the end of the presentation. He'll also introduce it by covering 3 case studies, 3 projects where this new material has been installed in Chile, South Africa, and Egypt. So, by way of an introduction to the company and the material, by way of a bit of background, Concrete Canvas was set up by myself and Peter Bruin, who's the other director and co-founder of Concrete Canvas, a long time ago in 2005. It's a spin out from Imperial College, London, where myself and Pete met. We're both engineers. As Ian said, mechanical engineering. I studied at Bristol and Berkeley, and Pete at Cambridge. And the slide you can see is the original concept sketch behind the idea that led to the development of the concrete canvas material. So this idea was to create inflatable concrete buildings for disaster relief. It's a very simple concept. The idea was that if we could create an inflatable plastic liner, and on the outside of that liner bond a fabric that was filled with a dry concrete powder, and prefabricate it together with steel doors and fold it up into a plastic sack, that would then be a way of creating a structure which could be rapidly deployed for disaster relief and emergency situations. So this is what the concrete canvas shelters look like pre-deployment. This is the sack that's delivered to site. It comes with a inflation unit, which is electrically powered. Once it's plugged in about 20 minutes, the structure unfolds and inflates. Once it's inflated, the concrete-filled fabric on the outside can be sprayed with water. That water then hydrates the high early strength concrete powder, and in 24 hours, the concrete fabric on the skin of the shelter has set. You can release the pressure from the inflatable liner, and you have a hard concrete, fiber reinforced concrete, durable structure that will last for over 10 years. And the liner remains in place inside to provide a sterilizable working surface. So this is the concept we had at university back in 2004. In 2005, we set up the business on graduation, and we then spent 2 years getting the material to work to a point where it would work for the purposes of creating these rapidly deployable structures. And in that process, we realized that the material that we invented to make the shelters work actually had a huge range of applications outside of emergency shelters. And in fact, the business has grown off the back of the material. And although we manufacture and sell the shelters now, they're a very small part of what we do. So we spent 2 years in Northampton developing the product. And then in 2007, we moved to the current site in South Wales, which is where we're currently based. to develop the production equipment. And one of the challenges with developing a new material technology is that there's no manufacturing equipment available to make it. So we then spent the next 2 years designing and building bespoke manufacturing equipment to produce GCCMs in the volumes and to the quality that we needed in order to make it commercially viable. By 2009, then we started commercial production in large scale, and were able to start introducing the material for a wide range of civil infrastructure applications. And the reception is it's traditionally a very conservative market, selling into infrastructure and into the engineering and construction sector, but it was very warmly received, and by 2014 we were actually the second fastest growing manufacturing business in the UK, named in the Sunday Times Fast Track 100. So as the company's grown, we've continued to introduce it into new markets and new applications, all the time the focus being on the material rather than the shelters. And the latest expansion was to a new site last year in Pontyclean, down the road from Treforest. So this is an 86,000 square foot space, giving us the capability to expand our production for the future demands and the needs that we're seeing from the market. And part of that is to allow us to put in the production line for the new product, which Simon is going to introduce. That has been brought about because we've continued to invest very, very heavily in R&D. You know, innovation is very much at the heart of everything we do. Myself and Pete are engineers. We're passionate about engineering and technology and innovation, and we see it very much as the future of the business. And that since probably 5 or 6 years ago, we've been developing this new product line for irrigation, and we're now in the position where we can start rolling it out and introducing it to the market. Currently, about 85% of everything that we manufacture is exported, so we've got quite a wide global footprint. We've got offices in 6 countries outside the UK, most recently an office in Houston in the US, where we've got a team of 4. But we have sales partners in about 60 countries around the world. And we've got a very good interactive case study map on our website as well. So you're able to go onto our website and have a look at some of the installations and different applications that the material is being used for in different countries. Here's a bit of a flavour for some of the consultants and contractors we've worked with in the UK, and obviously some of the companies in the international markets as well. So traditionally, this tends to be in civil infrastructure, petrochemical, and mining. But as I say, we've launched CCX now to start looking at new markets, namely the irrigation sector. So what is concrete canvas? What is this material? Apart from being the fabric that was developed in order to get the concrete canvas shelters to work? Well, essentially, it's a flexible polyester geotextile. It's a 3-dimensional fiber matrix, and it's filled with a high early strength dry concrete mix. One surface is porous, and that's the surface that it's hydrated through, and then the rear surface has a waterproof PVC coating. The material, as it's supplied, comes in a roll, and it's flexible, and it's very simple to use. You simply unroll it, lay it over the earth structure you want to cover, and once it's fixed and jointed, you spray it with water, activating the concrete mix, and in 24 hours it sets hard. And this material is now part of a new class of material as defined by the ASTM committee of GCCMs, geosynthetic cementitious composite mats. Concrete canvas is available in 3 formats. So the standard format is what we call a bulk roll. So this fits on a standard ISO pallet that makes it very easy to ship around the world. And this fits up to 200 square meters of concrete lining on it. We can also manufacture it, and we supply it in man-portable rolls or batched rolls, which are used for installation in hard to access areas. And then more recently, we've been manufacturing it in what we call wide rolls, which are typically 2 or 3 times the standard roll width. So that's a 2 or 3 meter roll width. So those are the formats. It also comes in 3 different thicknesses, depending on the application. So CC5 is the thinnest product, it's 5 millimeters. And this is generally used for applications with very little surface water flow. So for example, covering slopes or for lining bunds. CC8 is the middle product, 8 millimeters, and this is traditionally used for lining channels, typically for drainage. And then CC13 is the thickest product, and this is typically used for high impact or for protection applications. So cover now very quickly some of the reasons why this material is being used. So principally, the primary benefit of GCCMs is the speed of installation. So concrete can now be unrolled instead of having to be sprayed or using poured or shotcreted. So it's typically 10 times faster, up to 200 linear meters can be laid in an hour. And one of the projects I'm going to talk through just before I hand over to Simon is a canal in Chile, the Bella Vista Canal, which highlights really well where this material can provide a benefit against conventional concrete. The second reason CC or GCCMs are often used is the ease of use. It's much simpler because you don't need any training, there's no compaction, there's no leveling, you simply spray with water. It also can be installed in wet weather, and it has a very low logistical footprint. So to illustrate that, this slide demonstrates it very well. So for example, a single pallet of concrete canvas, as I say, can surface around 200 square meters, and that's equivalent in 100 millimeter surfacing of around 2 17-ton ready-mix trucks. So for erosion control type applications, a single pallet can replace typically 2 ready-mix trucks. So there's a big benefit in terms of logistics. And because of the speed and ease of installation, there's also lower project costs. So typically CC provides a cost saving of around 10 to 15% over conventional concrete. And finally, there's an environmental benefit. So partly that is because of the transportation, but mainly it's because of the embodied CO2, because instead of pouring 100 or 150 millimeters of concrete, you're laying now just 5, 8 or 13 millimeters. So we've had an independent life cycle assessment to 14,040, and that shows that the embodied carbon life cycle saving is around 55% compared to an ST4 concrete. So where is this used? We're going to talk about irrigation channels specifically, but more generally, it's used in drainage channel lining, slope protection, where the surface needs to be protected from surface runoff and surface slip, bund lining in petrochemical installations for secondary containment, and lining of cracked or damaged concrete structures, channels, or containment structures. And here there's a real benefit because you're able to reline a structure, providing another 50 years, 120 years of life, but without affecting the flow capacity of the channel, because you're only adding a few millimeters of thickness. So you maintain the flow characteristics. And then many others, such as weed suppression, culvert lining, gabion reinforcement. And we believe we've only just scratched the surface, to be honest, of where this material is used. So I'd now like to move on to a few case studies, which I think are relevant and sort of provide a bit of an insight as to how we've gone on this journey from emergency shelters to erosion control applications towards the irrigation sector. So this is a project completed in 2017 in Chile, in the Bella Vista region. It's an irrigation channel installed by one of our partners called Pacifictech, who's in place over there. The problem they had in the Bella Vista Canal was that the channel had been cut into soil and rock, and unsurprisingly suffered from a high degree of water loss, and that reduced obviously the water supply available to the local community. There were 5 sections of the canal that were identified for improvement, but they were all in very difficult to access locations. Another key challenge on the site is that they had a very limited period where they could cut off the water supply. So there was only 8 days that they, at any one time, they could shut down the canal for a period of 8 days. And this could only be done over a very short period during the winter months, so that they didn't risk damaging the local community crops. The solution that was selected was the CC5 material, and this was based on the speed of installation compared to conventional concrete, and the ability of the batched rolls to be transported to the sites with very, very limited access. You can see on the photo, it was very hard to get heavy machinery onto the crest of some sections of the channel. The first phase of this project was completed in only 5 days by a team of 6, covering 600 square meters. This included all the ground preparation, which was substantial, reprofiling, and the laying of material. And then based on the success of this first phase, it was decided to go ahead with much more substantial second phase covering 2.4 kilometers. And for this section, a much more uniformly graded profile was required. And so a new method of ground preparation was used. This involved using a trapezoidal formwork that you can see in the photo. I've got a video that will show it a bit more clearly. And this was used to basically profile the ground with compacted stabilized material being inserted behind the former. And this allowed the profile and the fall of the canal to be very well controlled. And then the CC5 bulk rolls were then deployed on site from a spreader beam, from an excavator, cut to length, laid, fixed into the anchor trench with pegs, and then jointed with screws and a sealant. The overlaps of the layers were in the direction of water flow, so shingled and overlapped by 100 millimeters. So I've now got a very short video, which I hope will work okay. Excuse me, there we go. So due to the logistical challenges of only being able to work for 8 days at a time, a team of anywhere up to 70 installers worked on the project at any one time. So over the entire 2.4 kilometer section, there were 3 teams, including the groundworks. They had 11 backhoes, 3 excavators, spreader beams. So while one team worked on regrading and preparing the substrate, Another team was laying the material on a section that the preparation team had just completed. And then the third team worked behind them, hydrating the completed installation and so on. And this allowed the installation to progress at a much quicker rate than it otherwise would. So using this method, a total of 18,000 square meters of CC5 was installed in 40 days, with the team working around 9 hours a day. So this is all driven by the very short cut-off time that they had to stop the water flowing in between installations. So there's the finished project. And I just want to, just before I hand over to Simon, to give you a bit of a flavour of the scale of some projects that we've installed. This was a channel in Argentina. It's a 50-metre wide channel, over 20,000 square meters of material. And here you can see the material in service. I won't go into too much detail, but it was a very demanding job. The client was a nuclear power plant, and so there was very high requirement both in terms of the specification and installation on this project. So I'll now hand over to Simon, who will introduce CCX, and hopefully the projects I've shown you, particularly the one in Chile, have given you a bit of an idea of why we started to look at how we could develop a material specifically for the irrigation sector. Over to you, Simon.
Thanks, Will. Good afternoon to everybody. And I would just like to echo Will's gratitude to Ian Todd and the IWF for this invitation to present this afternoon. So my part of the presentation today will look at a brief synopsis of canal lining. I will introduce you to our new product for bulk water infrastructure with a product overview thereof, and then finish with a commercial cost analysis and some case studies. Just to reiterate some of the comments that Ian made at the beginning of the presentation, by definition, canal lining is the process of reducing seepage loss of irrigation water by adding an impermeable layer to the face of a trench. Seepage can result in significant losses of irrigation water from canals, so adding lining should make irrigation systems more efficient. Canal linings are also used to prevent weed growth, which can spread throughout an irrigation system and reduce water flow. Lining a canal can also prevent waterlogging and salinization of surrounding low-lying areas of the canal. Lining can also reduce maintenance costs associated with the canal network, as well as improve the reliability of water distribution through this network. The two most important functions of lining, though, are reduction of seepage losses and improvement in hydraulics, both of which have a direct financial benefit typically to the ultimate water user. There are a number of factors that influence seepage losses through a canal. Seepage is primarily attributed to the permeability of the soil subgrade and the chemistry thereof. But there are also compounding factors like the canal geometry and head of water within the canal, the position of the water table adjacent to the canal, the type of lining used in eliminating seepage, the quality of construction when installing this lining, the age of the canal infrastructure, and the maintenance regimen conducted on the canal network itself. In order to counteract seepage, there are a number of factors which need to be taken into account when selecting a lining solution. These factors are typically summarized into structural stresses, which are associated with hydrostatic forces, and these can be substantial and need to be transferred into the subgrade effectively. Unbalanced hydrostatic pressure on either side of a liner can cause damage if not given adequate consideration, and point loads induced by maintenance and animals must be considered during canal service life. The durability of the lining given the service life conditions should also be considered, and thermal expansion and contraction as well as shrinkage is a force that is especially prevalent in concrete lining. Soil movement and dispersion must be known prior to selection of a liner, and there are a number of other factors that need to be taken into account too. Based on these factors, there are a number of canal lining solutions that are used, with selection typically hinging around durability and impermeability. These are summarized into, firstly, rigid linings like cast in situ, precast, or sprayed concrete that demonstrate a high degree of durability, flexible and permeable linings like polymeric BGMs and others, which are typically selected for their high degree of impermeability and can be installed as exposed or covered elements, and stabilized earth, which requires treatment of soil to increase its strength, density, and impermeability. There are, however, a number of pitfalls to each individual lining solution. There are, however, a number of pitfalls to each individual lining solution. Rigid liners are affected by climatic conditions such as freeze-thaw weathering, which causes cracking or movement of adjacent panels relative to one another. Subgrade conditions like expansive soils, for example, also influence service life performance, whilst quality of construction can be a major contributor to lining longevity. In the case of geomembranes, exposed solutions are vulnerable to climatic conditions, vegetation growth, vandalism, animal and human degradation, as well as maintenance activities. Covered solutions are very effective, but can be time-consuming to install or expensive given the multiple components required. And stabilized earth solutions are typically the most prone to poor construction and permeability and require regular maintenance to ensure design functionality is retained. In 2002, the US Bureau of Reclamation conducted a 10-year trial on 34 canals across 11 irrigation districts in the US. 4 main categories of lining were considered, namely fluid applied membranes, concrete alone, exposed geomembranes, and geomembranes with concrete top cover. A benefit cost analysis was then conducted with durability, maintenance, cost, and effectiveness at reducing seepage being the major attributing variables. Considering these variables, concrete covered geomembranes were shown to provide the best value for money when lining canals. So in consideration of the factors associated with effectively lining irrigation canals, we have developed a new product called CCX that can completely counteract seepage losses whilst maintaining a very high degree of durability. Please enjoy the short elevator pitch introducing you to CCX. So we're just moving back to the presentation. Next slide, please, Will. Thank you. So in terms of product overview, what does CCX look like and how will it perform? Sorry, Will, I think you've gone one slide too far. There we go. In terms of product overview, what does CCX look like and how will it perform? CCX has utilized 15 years of concrete canvas technology in developing a product tailored for lining of bulk water infrastructure in both new and remedial applications. In terms of structure, it is composed of the following components: a UV stabilized polyester top surface and polypropylene bottom reinforcement layer are stitched together and filled with a high density ordinary Portland cement mix. Density of the OPC mix ensures optimum water powder ratio in all hydration conditions for exceptional performance. The LLDPE geomembrane laminate is fused onto the polypropylene bottom reinforcement layer to create a highly impermeable, high performance composite. There are two CCX variants available for bulk water infrastructure applications. Both have been named to conform with the common classifications for GCCMs and GCCBs. CCX Matte is hence classified as a GCCM and CCX Barrier a GCCB. CCX Matte has a 0.3 millimeter thick LLDPE backing that is more suitable for low water head infrastructure or for remediation or top cover of existing line canals. CCX Matte is continuously laminated with a 0.3 millimeter thick membrane that is jointed in a similar fashion to conventional concrete canvas products as per the typical detail on screen. CCX Matte can be thermally bonded or an adhesive used to enhance impermeability of the joints, but is not completely impermeable. The second variant of CCX is CCX Barrier, which has a 1 millimeter thick LLDPE backing with a separation between the laminate and bottom layer on one edge only. By peeling back the top cement-filled geotextile layer, the geomembrane is exposed. This allows for thermal welding of the geomembrane layer, making CCX Barrier more suitable for larger infrastructure or applications requiring greater impermeability and certifiable joints. I'd now like to share with you a short video we have put together for CCX Barrier, demonstrating the geomembrane backing thermal welding and overlapping process in order to attain a completely impermeable and durable joint detail. Please bear with us for a second. We'll just go back to the presentation. So both CCX mat and barrier are designed to meet the minimum specification of ASTM D8364 for type 2 GCCMs as per the table on screen now. In terms of service life performance, there are a few key components to CCX that ensure it complies with the fundamental criteria for lining of a canal. Firstly, in order to combat seepage, CCX barrier has a permeability coefficient in line with common geomembranes in the order of 1 × 10⁻11 meters per second. Of course, impermeability of the material itself is not the only requirement for elimination of seepage. The welding testing and certification of CCX barrier joints has been designed to adhere to air channel test parameters taken from GRI GM6 for geomembranes. Secondly, in terms of durability, the flexural, compressive, and tensile strength, as well as abrasion resistance of CCX, ensures that it will attain a minimum design life of at least 50 years. Thirdly, the Manning's roughness coefficient of CCX is equivalent to a floated concrete finish, ensuring that the capacity and throughput of a canal can be optimized and made as efficient as possible. And fourthly, a rather unique characteristic of CCX is its differential settlement capacity. Being a relatively thin element gives CCX the ability to flex and conform to changes in subgrade conditions caused by chemical or seasonal changes. At 10% strain, that is 100 millimeters per 1,000 millimeters of surface area, the concrete-filled geotextile element of CCX will have the ability to deflect by as much as 197 millimeters prior to rupture and exposure of the geomembrane backing. The three-dimensional fiber reinforcement of CCX allows for the strain whilst distributing stresses through microcracking without the propagation of a single large crack. In terms of manufacturing format, CCX is 1.9 meters wide. It is 10 millimeters thick. It weighs approximately 15 kgs per square meter, with stock roll lengths being typically 50 meters. Maximum annual output capacity is anticipated to be around 4 million square meters per year, giving us the ability to support some of the canal lining mega projects that are out there. For export purposes, we have determined that a 20-foot container has the capacity of approximately 1,200 square meters, whilst a 40-foot container has a capacity of around 1,500 square meters based on a stock roll length of 50 meters. We also have the capability to fabricate bespoke roll lengths to suit specific cross-sectional profiles. So to revisit the benefit cost analysis associated with the 10-year USBR study, we have conducted a cost analysis for a specific project in Colorado, USA for the USBR. We used current market rates and installation costs to determine how CCX barrier would compare to the previously studied lining solutions. The following assumptions were permissible: that CCX has a design service life minimum of 50 years, that the maintenance costs of CCX would be the same as a concrete lining, and that the effective seepage reduction percentage would be the same as a geomembrane. It is evident from the analysis that CCX barrier has a significantly improved benefit cost ratio when compared to all other lining solutions used. It is also evident that the cost of CCX barrier is slightly more feasible than concrete lining alone. And whilst we appreciate that conditions and costs will vary around the world, we are confident that the utilization of concrete canvas CCX will have significant benefits for most canal lining projects when compared to the alternatives. I would like to finish off by showing you a few case studies from trial projects conducted with CCX to date. So Will is just going to switch over to another video quickly. Well, if you can just turn the volume down on the video. Thank you. In September of 2020, we conducted our first international CCX barrier trial on a canal in Atfia, Egypt. The trial was for the Egyptian Ministry of Irrigation with the close attention of the Egyptian Army. The installation was carried out in very testing conditions with temperatures between 35 and 40 degrees Celsius. Approximately 75% of the water transported through these canals is lost to filtration. The sides of the canals are also eroded away and deposited in the floor of the canal, resulting in widening and creating greater water loss to evaporation. CCX barrier was installed to an approximately 8-meter wide profile over a 50-meter length of the canal. The overlaps were thermally bonded and fixed with adhesive to create a highly impermeable joint. The aim of the trial was predominantly to determine the speed and ease of installation of CCX using readily available local labor and equipment. As you can see in the video, construction in the farming communities is very basic, with unskilled labor sourced from local communities. CCX barrier was lifted into position and aligned transversely to flow in the canal by excavator. A double width spreader beam was used to deploy the 20-meter long by 1.9 meter wide rolls, which weighed approximately 600 kgs each. Material was drawn off the spreader beam by hand using a rope and labor positioned on the opposite bank of the canal. A concrete cutting disc was then used to cut these rolls to length. The LLDPE membrane backing is very smooth and has a low coefficient of friction. In order to stop the slipping of CCX barrier into the canal during the alignment and jointing exercise, a temporary peg was installed within the anchor trench midway between the overlaps. Sandbags were also used as ballast to ensure close conformity to the underlying profile. The cement-filled geotextile overlaps were fixed either by thermal bonding or by adhesive. Both methods provided significantly good results in terms of strength and impermeability and were demonstrated effectively during the trial. Once all jointing had been carried out, the overlaps were pegged within the anchor trenches and hydration began. Hydration was carried out at 15-minute intervals due to the high ambient temperatures, as well as the drying effect caused by wind. The material was hydrated 3 times at these 15-minute intervals to ensure saturation, and then a final hydration made at the end of the day's work. Upon completion of the initial 3 hydrations, the anchor trenches were backfilled and compacted by hand. And the approximately 400 square meter trial was completed by a team of 10 installers in less than a day and was a very successful demonstration of speed and ease of installation. Thanks. We'll just go back to the last couple of case study slides. So the second case study I would like to show you is from the Pusela irrigation scheme in Limpopo province, South Africa. This canal lining trial involved the remediation of 50 meters of canal with CCX mat. CCX mat was laid longitudinally along the length of the canal and the sides buried in shallow anchor trenches and pegged at 2-meter intervals. Internal fixings 100 millimeters from the top of the underlying concrete structure were installed at 400 millimeter spacing to ensure close conformity to the underlying profile. The overlaps were thermally bonded and penetrations were sealed with epoxy to create a highly impermeable liner. The remediation of this canal was completed in the space of only 2 hours by a team of 4 installers. Our third case study is from Chile, where 80 meters of canal required remediation of an existing stone-pitched U-shaped canal in a shorter time frame as possible. The trial was used to demonstrate the speed and effectivity of CCX mat for remediation of U-shaped canals. Overlaps were thermally bonded to enhance impermeability, and 19 millimeter screws were installed at 100 millimeter spacing to enhance mechanical joint strength. The selection of screw length was made so as not to penetrate the underlap geomembrane backing. And approximately 250 square meters of canal was lined in a very inaccessible area over the course of just 2 days. And finally, the last case study I'd like to share with you was conducted on a dairy farm in Wales in September of 2020. We often get asked by canal clients how susceptible concrete canvas is to cattle and other animal hooves when they make their way to the canal edges to drink water or attempt to cross a canal. This case study was simulated to determine how CCX would perform in this scenario. Hence, CCX was used to create a pad for testing of puncture resistance on a dairy cattle pathway. A pad of 2 by 2.5 meters wide was lined over a compacted soil platform. Each day, 400 cows pass over this pad twice in the morning and twice in the evening, going to and from the dairy for milking. The pad was open to trafficking within 24 hours of installation and has received in the vicinity of 500,000 hooves passing over it to date. Considering a dynamic point load in the region of 3 kilonewtons per hoof, there is barely a scratch on the CCX surface and no evidence of cracking to date. This test clearly demonstrates a high propensity to puncture resistance of CCX. So that concludes my presentation and introduction of CCX. I'd now like to hand you back to Ian and answer any questions you may have. Thank you very much.
Okay, well, thank you, Simon and Peter, for your very comprehensive presentation of concrete canvas and also very good examples of where it's being used. I can't see too many questions in the chat. Oh, it seems to be a bit. Yeah, anyway, well, I'll start off the questions by questioning about the cost, because I mean the problem with canal lining in most places is a relatively high cost of it. How does the cost of your concrete canvas compare to these conventional methods?
Well, I think if we use the US Bureau of Reclamation case study as an example, we are very competitive when compared to composite solutions like geomembranes with concrete top cover. In fact, we've demonstrated that we are definitely more feasible than composite lining solutions. Obviously, it varies around the world. You know, for example, countries like Uzbekistan, where importation costs might be quite high due to it being severely landlocked, we may be less feasible than other lining solutions. But certainly in most countries around the world, we are extremely competitive with when compared to geomembrane and concrete top cover. And very often when compared to just concrete as a standalone lining solution, we are also very competitive. So it's difficult to give you exact figures on costing because you need to consider factors like shipping costs, duty costs associated with certain countries. But as I say, in most instances, we are more feasible than other lining solutions.
Okay, thank you. I mean, you manufacture the panels in Wales and you export them throughout the world. This is the only place you manufacture them is in Wales.
That's correct.
And where did you get your geosynthetic membranes from? Are they sourced locally, or are they specifically made for you, or are they just general products that you're using?
So the geotextile is sourced in the UK, as are the cementitious components, and then the geomembrane, the waterproof component, we manufacture that in-house.
Oh.
So that's extruded directly onto the back of the product. And one of the benefits of doing that is you get really good adhesion between the geomembrane and the concrete. Oh. So that's an in-house manufactured component. It's from geomembrane grade resin, and it's manufactured to geomembrane standards. So we have, and we are going through the process of getting the product certified to relevant European norms and ASTMs.
Oh, okay. Does anyone else have any questions for the speakers?
There's a hand up from Jeremy.
Yeah, hi, William and Simon. I was interested, well, the cost question was one that I was interested in, but just in terms, you mentioned earlier on one of the problems of external or hydrostatic pressure, and I'm just wondering for a irrigation canal which is on rotation, you know, large irrigation canal on rotation, which is filled and emptied regularly, whether there's any issues there with in areas of high groundwater. That was one question, and the other one really more relates to if any of the installations you've had in irrigation canals, there's any sort of independent research going on to evaluate the lining, the CCX. Thanks. It's very interesting, really interesting presentation. Thanks.
Thank you. Well, perhaps I can answer the first part and you can answer the second.
Mm-hmm.
So when it comes to hydrostatic pressure, you know, from groundwater pressure, the best mechanism for dissipation of that pressure is a subsoil drainage network. And we have developed a couple of techniques for incorporating subsoil drainage systems into the actual lining, so that, you know, that force can be dissipated through a pop-up valve, essentially. We've got potentially two solutions for subsoil drainage. And when the canal specifically is empty and you get rapid drawdown of, you know, water and groundwater, that valve will open up and allow the flow into the canal itself without damaging the lining.
So a lot of the same methodologies and techniques that are used at the moment to dissipate groundwater pressure, either with geomembranes or with concrete, essentially. So nothing revolutionary there. It's using a lot of the same systems which are already in place for dissipation of groundwater into the canal. I can jump on the second question, which was about independent evaluation. So this is a material we're in the process of launching at the moment. We've got a number of installations. Simon ran through a few of them in Chile, South Africa, Egypt. We've got a number of more trial and demonstration projects happening over the course of the next few months. The rollout program has been slightly hindered, obviously, because of COVID, but something we're very keen to do is work with local governments, local ministries of agriculture and irrigation, and also with the members of ICID and IWF. So, you know, we'd welcome if any of the attendees on this presentation have any recommendations for organizations or projects. We'd be delighted to hear from you, because we're aware this is, you know, it's a big area. It's not something we have a huge amount of experience in, and we would love to hear from members of ICID and to work with you to get some field experience and get CCX in the ground and get it trialed.
Yeah, thanks. It's interesting. I mean, yeah, interesting. You mentioned Uzbekistan, because that's somewhere I've been working recently, and when there's, I know the Asian Development Bank is looking at modernization projects and in fact looking at beautiful linings with solid concrete cover to it, and this would be an interesting experiment to put in side by side with that, with some sort of independent evaluation by maybe there's many research organizations there. So yeah, that would be an interesting case study.
Yeah.
Thanks.
Yeah, no, definitely. Jeremy, please, you know, we put Simon's email address up at the end. We can maybe put that up as a holding slide once the questions are finished. So feel free to get in touch, or maybe Ian can share details after the presentation.
Well, just to add to that, Jeremy, we are actually planning a trial in Uzbekistan for the end of October, and it will be in conjunction with a couple of the ministries and irrigation authorities, and it will be in Tashkent, so it will be very accessible. And if you are in Uzbekistan at the time, we would really appreciate your attendance. So please feel free to get in touch with us, and it would be great to get your input.
Yeah, thanks. Unfortunately, I won't be there, but certainly I can, if you send me some details of the trial, I could certainly send that on to some of the people I know there in the Water Resource Ministry and the International Water Management Institute as an independent research group, and the local ADB officers who are doing, you know, some of the specifications for this work. I'll put my email in the chat. Thanks a lot.
Thank you very much.
Thank you, Jeremy.
Appreciate it.
Okay, well, thanks, Jeremy, for your question. I think we'll have to come to a stop because we overrun slightly, and I see some have left. So I am a bit disappointed by the number of people here today. So I will try to find out as to what it is. But as I say, we'll put the recording on the IWF website, and we'll try to bring in a wider audience, because I think it was a very comprehensive presentation you gave, and I would like to thank you. But before I close, I'd like to point out that the next IWF event is on the Mekong, discussing the Mekong River in November the 5th and 12th. It's in a two-part virtual meeting, and it will run from 9 in the morning to midday on these days. The theme of the meetings is the Mekong Basin implications of a rapid transformation of a transboundary river system. And I think we have eight speakers on that, 4 in each day. So please come along to that. And more details of that can be found on our website. So finally, on behalf of IWF, I'd like to extend a very hearty vote of thanks to the speakers, William Crawford and Simon Lester from Concrete Canvas Limited, for describing their very interesting and important work and for sharing their findings and opinions today on a topic that continues to be a challenge for designers and operators of canals. So thank you very much for that. And also to all the participants, thank you for joining us. Have a nice evening, and we hope to welcome you back soon. So thank you very much, all of you.
Thanks, Ian. Thanks, everyone.
Thank you, Ian.
Thanks a lot.
Much
Bye.
appreciated.
Have a good evening. Thank you.